of numbers that is going to allow us to solve such equations. Now, this is the set of complex numbers, and it is denoted by this symbol. And it is basically the set that contains the set of real numbers and the set of the imaginary numbers. These imaginary numbers are denoted by I, and they're said to have the property that I squared is equals to -1. By combining both the imaginary number and real numbers, we can define a complex number, which is formally expressed as z is equals to a plus bi. Here, the values of a and b are regarded as real numbers, and from I squared equals to -1, we see that I is equals to square root of -1. We refer to a as the real part of the complex number, and b is called the imaginary part of our complex number. Now, a complex number in the form a plus bi can also be identified as an ordered pair and thus be represented on the complex plane by the point AB. This complex plane is also referred to as the Eigand diagram, where the horizontal axis is called the real axis and the vertical axis is referred to as the imaginary axis. For example, if we consider a complex number given as 2 plus I, we see that a is equals to 2 and b is equals to 1. Thus, this complex number can then be expressed as the point 2, 1. Basically, we see that a goes 2 units to the right in the direction of the real axis, and b goes 1 unit up in the direction of the imaginary axis. A complex number in this form, a plus bi, is called rectangular form. In some cases, they refer to it as the standard form or the real and imaginary form. And we note that every real number is a complex number where the imaginary part is 0. For example, if we consider z equals to 5, 5 is an element of real numbers and can thus be expressed as 5 plus 0 I. For our complex number a plus bi, if it happens that the value of b is not equals to 0, but a is equals to 0, then we have what is called a pure imaginary number. And this is plotted on the imaginary axis. So if we consider z is equals to -I, we agree that the value of b is 1. So on your complex plane, we are going to move 1 unit downwards in the direction of the imaginary axis, and we do not have any values for x, so our complex number lies on the imaginary axis. And then we have more examples of complex numbers plotted on the complex plane. Again, it's also referred to as the Eigand diagram, so you can look out for that. Right, we note that all the basic operations like addition, multiplication, subtraction, and division that we are used to when dealing with real numbers also holds in this case. In particular, we can add or subtract complex numbers together to get a new complex number. To do this, we are going to add the imaginary parts together and the real parts together and combine them. For example, let's let z to be the complex number defined by a plus bi. And then we have another complex number w, which is given by c plus di. Then z plus w will be a plus bi plus c plus di. Then this, by grouping your like terms together, like we said, we will add the real and imaginary parts separately and combine them. We see that a will be added to c, and then we sum bi with di. Since I is common here in both terms, we can factor it out to write the imaginary part as b plus d, and then there's our imaginary number, and the real part of this complex number is given as a plus c. And then we get the same results when we are dealing with subtraction. If Z is still the complex number A plus BI, and then W is the complex number C plus DI. We see that when we take or calculate Z minus W, we'll get A plus BI minus C plus DI. Then subtracting the imaginary parts together and the real parts together gives us A minus C as the real part of Z minus W, and we get B minus D as the imaginary part of Z minus W. Same thing can also be done for multiplication. You can take the product of complex numbers to get a new complex number. So if we have Z, which is given as A plus BI, and then we have W, which is given as C plus DI, then Z times W is simply A plus BI multiplied with C plus DI. Here, when we expand, we are going to get AC minus plus ADI plus BCI plus BDI squared. And if we recall, we said that I squared is given as -1. So if you replace I squared with -1, this expression becomes AC plus ADI plus BCI plus BD, which is then multiplied by -1. This term then becomes real. BD times -1 gives us negative BD, so we'll get AC minus BD as the real part. Plus, I is common in both terms, so we can factor it out to get AD plus BC as the imaginary part of Z times W. And then we have a few examples to look at. For the first one, we are given Z is equals to 2 minus 7i. And then we have a second complex number, which is given as 4 minus 4 plus 2i. To add Z with W, again, you're going to add the real parts and the imaginary parts separately, and then combine the results. So we see that we'll get 2 minus 7i plus minus 4 plus 2i. Two minus 4 gives us -2, minus 7i plus 2i gives us -5i. And then for the second example, we are asked to calculate 1 minus I minus the complex number 3 minus 4i. Again, we are dealing with the difference of two complex numbers. So when you subtract one complex number from another, the result yields a complex number. When you subtract, or rather 1 minus 3 gives us -2, and then 1 plus 4 will give us 5. So the real part is -2 in that sense, and the imaginary part is +5. And then for our third example, they want us to take the product of Z, which is 2 plus 3i, with W, which is 4 minus 2i. Again, the procedure is still the same. 2 plus 3i times 4 minus 2i. When you expand, we see that we'll get 8 minus 4i plus 12i minus 6i squared. And if you use the fact that I squared is equals to -1 and substitute -1 there, then that term becomes real. By grouping the like terms together, we'll get 8 plus 6, which gives us 14. And then minus 4i plus 12i gives us 8i. The result then yields a complex number. Right. Every complex number, again, in the form A plus BI, for every complex number, we can define the complex conjugate. And this is simply denoted by Z bar, and it is defined as A minus BI. The complex conjugate is just the complex number where the imaginary part is negative. And we have expressed that the complex number A plus BI can also be expressed as a point on the complex plane. That means that the conjugate will also be defined on the complex plane, and we see that this is just the complex number AB reflected along the real axis. So for A plus BI, we have the point AB, and for A minus BI, we have the point A minus B. We use the complex number to help us define division of complex numbers. Again, we said that you can add or subtract two complex numbers together to give a complex number. Same thing happens with multiplication. When you take the product of complex numbers, you get a complex number. Now we'll do the same thing for division and show that if you divide one complex number with another complex number, the result then yield a complex number as well. Again, the general expression Z is equals to A plus BI, and then we have W, which is C plus DI. When we calculate Z over W, we are simply going to multiply both the numerator and the denominator by the conjugate of the complex number in the denominator. So we see that our complex number in the denominator is W, and W is C plus DI. That means that the conjugate of W is just C minus DI. Now to calculate Z over W, this is just A plus BI over C plus DI times, we multiply both the numerator and the denominator by the conjugate of the complex number in the denominator. In this case, we have C minus DI all over C minus DI. In the denominator, we see that we'll have C plus DI times C minus DI. When you expand this, we are going to get C squared plus CDI minus CDI plus D squared I squared. This then cancels out. We are just left with C squared plus D squared I squared. From here, you just need to remember that I squared is equals to -1. So when you substitute -1 here, then the denominator, we have -1 here. So when we substitute -1, the denominator then becomes C squared plus D squared. And then we take the product in the numerator. When you expand and simplify the numerator, we are going to get AC plus BD for the real part for the product in the numerator. And then we get BC minus AD for the product in the numerator as the imaginary part. Since the denominator is just any real number, then you can rewrite this as just AC plus BD all over C squared plus D squared. And that's the real part of Z over W. And then for the imaginary part, we'll get BC minus AD all over C squared plus D squared. And then there's our I. We will also talk about the inverse of a complex number, and this is simply denoted by this, and it's the same as saying 1 over Z. Since division of complex numbers is defined by just taking the product with the conjugate of the complex number in the denominator, then that is how we will calculate the inverse of a complex number. Again, the results will yield a complex number where the real part is just A over A squared plus B squared, and the imaginary part is just negative B over A squared plus B squared. We notice that the conjugate has some properties, so just stated a few here, but basically for the first one, we see that if you take the sum of two complex numbers and take the conjugate of the result, you will get the same result by first taking the conjugate of each complex number and then summing the results. For example, let's say we have Z, which is equals to 2 minus I, and then we have W, which is equals to 3 plus 2I. Z plus W will add the real part separately, so 2 plus 3 gives us 5, and the imaginary part separately. -1 plus 2 gives us +1, so we have I. Therefore, the conjugate of z plus w is just a complex number where the imaginary part is negative. So in this case, we get 5 minus I. And then we are going to check if the results hold. If z is equals to 2 minus I, it means that the conjugate of 2 minus I is just 2 plus I. If w is equals to 3 plus 2i, it means that the conjugate of w is just 3 minus 2i. Therefore, z conjugate plus w conjugate gives us 2 plus 3 is equals to 5. 1 minus 2 is equals to -1. So we multiply by I, and then we have 5 minus I. So the result indeed holds. And then for the second property, the idea is the same. The conjugate of z times w equals to the conjugate of z times the conjugate of w. And then we have another property here which says that if you have a complex number and you take it to the power n and take the conjugate of the results, you will still get the same thing if you first take the conjugate of z and then take everything all to the power n. These are just complex powers, and then we'll discuss them in just a few minutes. And then every time when we talk about the conjugate, we also mention the modulus, which is basically the distance from origin to our point. Remember we said that the complex number a plus bi can also be expressed as a point on the complex plane. So if this is just ab, then the distance from this point origin to that complex number is given by the square root of the real part squared plus the imaginary part squared. So say we want, or we have z equals to 2 plus I, and we want to find the modulus of z. This is basically the square root of the imaginary part. We see that the imaginary part in this case is 2, so we have 2 squared plus, sorry, the real part is 2, so we have 2 squared plus the imaginary part, which is 1, we have 1 squared, and this gives us the square root of 5, which is being the distance from 0, 0 to 2, 1, the point 2, 1. There are other several properties of the conjugate, but for this, in this case, we'll just simply show that these results hold. So from this point, if you take the square root on both sides, we see that the left-hand side will be the modulus of z squared, and then we take this to the power 2. Then this gives us a squared plus b squared. And you get the same result if you take the product of z with its conjugate. Right, and then next we will look into equations that gives us complex roots as the solution. So if we have real numbers a, b, c, and consider the quadratic equation ax squared plus bx plus c equals to 0, we know that we will use the quadratic formula to solve for such expressions. Now, if it happens that the value of this expression inside the square root is less than 0, then also, and use the fact that I squared is equals to -1, we will see that the square root of -y can also be, or rather it is equals to the square root of y times I. Thus, the results yield complex roots. We have an example on the next slide, x squared plus x plus 1 equals to 0, and they want to use the quadratic equation to solve for this. Since the value of a is 1, the value of b is 1, the value of c is also 1, you will simply substitute in the quadratic formula. Remember, this is just x equals to minus b. b is equals to 1 plus minus the square root of b squared. Since we have the value of b as 1 minus 4ac, both A and C are 1, you just substitute over 2A, we substitute the value of A, which is 1. Then we see that this gives us -3. So we have -1 plus minus the square root of -3 over 2. But remember, if you have the square root of a negative number, let's say x, this is just the square root of x times I. So we're going to get the square root of 3i. Already we see that the solution is complex. And thus we have two solutions, -1/2 plus 3/2i, or -1/2 minus square root 3/2i as the roots of the equation. And we can do the same thing for any quadratic equation and solve. Right, since we know that the polynomial or the general expression of a polynomial function is given by that, we notice that every polynomial of degree n is going to have n number of complex roots. For example, this question here is a quadratic equation, so it's a polynomial function of degree 2. Thus, the solution yields 2 complex roots. When you have a polynomial function of degree 3, you get 3 complex roots, etc. So basically, that's what the theorem is saying, that every polynomial function of degree n will have n complex roots as the solutions. Right, and then we get into another way of expressing a complex number. Since we said that a complex number of the form a plus bi can be represented as the point AB in the complex plane, then we should also be able to represent it by polar coordinates r theta. Here r is the non-negative distance from origin to that point, and theta is the angle that the line makes with the positive real axis. We may use these polar coordinates to identify any point of the complex plane, and we should be able to move from rectangular form to polar form, and from polar form back into rectangular form. Now from this, if we recall our trig ratios, we remember that cos theta in this case is given by the adjacent side over the hypotenuse. So we're going to get A over R. And sine theta is given by the opposite side over the hypotenuse. So this is just B over R. Thus, we can make A and B the subject of the formula to divide them as just R cos theta for A and R sine theta for B. Then the complex number a plus bi will then be expressed in polar form as just R cos theta, that's A. B is just R sine theta, and then we have our imaginary number I there. Since R is common in both terms, then Z is equals to R cos theta plus I sine theta, where R is just the distance from origin to our point. So remember, that's the modulus. So it will be calculated by the square root of the real part squared plus the imaginary part squared. And we're also going to use the fact that tan theta is equals to B over A, the value of B over A from the complex number A plus BI. The angle theta here is referred to as the argument of the complex number, and it is often written as arc of Z. And we note that the argument is not unique. In particular, if you have theta as arc Z, then theta plus 2k pi is also the argument that represents the same point. So r theta, the coordinates r theta and r theta plus 2k pi, where k is an integer, represents the same complex number on the complex plane. For example, we have the square root of 3 minus I. That's the complex number which lies in quadrant number 4. We have a positive real axis and a negative imaginary axis. So this lies in quadrant number 4. Then this complex number can be expressed in polar form as 2 cos 11 pi over 6 plus I sin 11 pi over 6. Now this one, we see that theta will be an element of 0 and 2 pi. Remember, this is the angle that our complex number makes with our positive real axis. So that is going to be theta in that case. We can also express this as 2 cos minus pi over 6 plus I minus pi over 6. Again, we have the same complex number, but in this case, the angle is here. So theta in this case is there. It's the angle that our complex number makes with the positive real axis. So this then goes back to what we were saying, that the argument is not unique. We're just simply expressing the same complex number, but it has different value of an argument. Right, and then next we're going to show how to convert from rectangular form to polar form. So the most obvious way in determining the argument is to first plot the complex number on your complex plane to see in which quadrant we are in. Now for this purpose, if we consider the fact that, or we restrict theta to be an element of 0 and 2 pi, we are going to observe the following rules based on the A-Gantt diagram. If our complex number is in the first quadrant, so if your complex number is in the first quadrant, it will be somewhere there. So I'll just put Z there. Then this is the angle, theta, that we are interested in. And the argument is just calculated by just taking arctangent of B over A. If it lies in the second quadrant, then our complex number is somewhere here. This is the argument. So to get the correct argument, we can simply calculate pi minus arctan of B over A. Remember, B is the imaginary part of the complex number and A is the real part. Same thing, if we're in quadrant number 3, our complex number will be somewhere here and our argument will be that. So that is going to be arc Z. And if we are in the fourth quadrant, our complex number is somewhere here, and we see that our argument is that, and we can calculate that by just by 2 pi minus arctan of A over B. Again, this is only true when theta is restricted between 0 and 2 pi. The argument is not unique, so you can choose any interval. And then you can find many arguments by expressing the same complex number. Now there are special cases. For a complex number A plus BI, if the value of A is greater than 0 and B is equals to 0, greater than 0 means A is positive, then the argument is equals to 0. Remember, if the imaginary part is 0, then our complex number lies on the real axis. So it will probably be somewhere there. Therefore, this is our angle 0, and then we have pi over 2, pi, 3 pi over 2, and 2 pi. So this can be 0, or you can also use 2 pi. If A is equals to 0, the real part is equals to 0, and the imaginary part is positive, we see that our complex number lies on the imaginary axis. So it is here, and the angle here is just pi over 2. If A is negative and B is equals to 0, our complex number lies on the negative real axis. So it's here, and this angle here is just pi. And then same thing. If A is equals to 0, but the imaginary part is negative, our complex number lies here, and this angle is 3 pi over 2. If you consider the negative part, you can also say that this is just minus pi over 2. It is the same argument, it is the same complex number, just a different argument. Right, so we'll look at an example. We have z is equals to minus 1 plus square root 3i, and then there's w, which is 1 minus I. They want us to convert these two complex numbers from rectangular form to polar form. Again, the general expression is equals to r cos theta plus I sine theta. So for z, we see that this complex number lies in the second quadrant. Since it lies in the second quadrant, the correct argument is this one. And from the rules above, we said that if z is in the second quadrant, then we are going to calculate the argument by just pi minus arctangent of, in this case, the imaginary part is square root 3, the real part is minus 1. And then for w, our complex number is in the fourth quadrant, then the correct argument is that one, when theta is between 0 and 2 pi. Therefore, for z, the argument is 2 pi over 3. For w, the argument is 7 pi over 4. And the modulus is basically the square root of the real part squared times the imaginary part squared. So for z, our modulus gives us positive 2. And for w, our modulus gives us square root of 2. Therefore, in polar form, we will get 2 cos 2 pi over 3 plus I sine 2 pi over 3 as a complex number in polar form for z, and square root 2 times cos 7 pi over 4 plus I 7 pi over 4 as the complex number in polar form for w. And then, like we said, all the basic operations like addition, multiplication will still hold. So we're going to show that multiplication, or rather how to determine multiplication of complex numbers in polar form. So the first complex number is defined as R1 cos theta 1 plus I sin theta 1. And the second complex number is given as R2 cos theta 2 plus I sin theta 2. To get Z1 times Z2, we will simply multiply R1 with R2 and we'll multiply the moduli and then add the argument. So R1 times R2 times cos theta 1 plus theta 2 for the real part, and then I sin theta 1 plus theta 2. And to derive the formula, it's very easy. Take the product of the two complex numbers, expand, use the fact that I squared is equals to -1, and then everything will fall into place. So we have the derivation here, Z1 times Z2, we have there's Z1, and then there is Z2. Since we're dealing with the product, then we can just simply take R1, R2 to the front, and then take the product of cos theta 1 plus I sin theta 1 with cos theta 2 plus I sin theta 2. When you expand that, we see that we'll have cos theta 1 cos theta 2 plus I cos theta 1 sin theta 2 plus I sin theta 1 cos theta 2 plus I squared sin theta 1 sin theta 2. Remember, we said that I squared is equal to -1. So when you substitute -1 where you see I squared, this becomes real. Therefore, you can group your like terms together. Since this part will be negative sin theta 1 sin theta 2, we see that there we'll get cos theta 1 cos theta 2 minus sin theta 1 sin theta 2. And then for the second part, everything is multiplied by I. Remember, I is common in both terms, so you can factor it out, and then we'll get something that looks like that. And then if we recall some of the trig formulas, we said that, or rather, we'll remember that cos A plus B is just cos A, cos B minus sin A, sin B. So for this part, we have cos theta 1, cos theta 2 minus sin theta 1, sin theta 2. So that can be written or simplified into cos theta 1 plus theta 2. And then for sine A plus B, we'll get sine A cos B plus cos A sine B. So we see that that part can then be written as just sine of theta 1 plus theta 2, which then proves the result that when you have to take, or rather multiply, two complex numbers in polar form, you'll simply multiply the two modulus and add the arguments. And then we have an example here. Z is given as the square root of 3 plus I, and W is given as minus square root of 3 minus I. Calculate Z times W in polar form and also in rectangular form. Again, in polar form, you need two things. You need the argument and you need the modulus. From the rules above, we see that square root 3 plus I is in the first quadrant. So the argument is simply calculated by arctan of 1 over square root 3. And this gives us pi over 6. Always remember to have your calculator in radians so that you can get the the correct angle. And then minus square root 3 minus I is in the third quadrant. So there is the argument. But remember, from this to that is pi radiant. When you calculate arctan of minus 1 over the square root of minus 3, we get pi over 6. But the correct argument is from this point to that. And from here to there is just pi over 6. So you will simply add pi radians with that angle, which is what we described above. And this will give us the correct argument as 7 pi over 6. Thus, in polar form, again, the product is to add the idea is to add the two, take the product of the two modulus and then add the argument. The argument here is pi over 6, 7 pi over 4. So you add them, and then this simplifies into 4 cos 4 pi over 3 plus I sin 4 pi over 3. And then in most cases, you will be asked to leave the answer in standard form. So to do that, you will take the product of 4 with cos 4 pi over 3. Remember, we said that A is equals to R cos theta and B is equals to R sine theta. And therefore, the complex number is just A plus BI. There's the value of R. There is cos theta. There's the value of R, and there is sine theta. And then you should be able to get the complex number in standard form or rectangular form. And then if you do it manually, we see that we'll get minus 2 square root of 3i, and this will give you the same answer, whereas when you convert from polar form to rectangular form. And then also for division, we are no longer multiplying R1 with R2. We are now dividing R1 by R2. And when it comes to the argument, we are no longer adding them, but now we will subtract theta 2 from theta 1. And to show that this is true, or rather the derivation is from the fact that division of complex numbers, you will multiply both the numerator and the denominator by the conjugate of the complex number in the denominator, and you should be able to get the same results and show that this holds. So this is the derivation is left in this case. If you want to, you can verify as an exercise that you get the same formula. And then next we'll get into the last part, which deals with powers and roots. So let us assume that we are given some complex number z is equal to a plus bi, and we want to find z to the power n. Now, if you do that manually, it can get messy and tedious, and it won't be nice. especially when n is positively large. For something like z squared, it's quite easy. You multiply the same complex number with itself, expand, simplify, and then you get the complex power. But in the case when n is positively large, it's very, it can get very tedious. So we will then apply the theorem. There's a theorem that helps us to calculate complex powers very nicely. This is called the Moever's theorem, and works for complex numbers in polar form. So if z is equals to r cos theta plus I sin theta, to calculate z to the power n, you will simply take your modulus to the power n and multiply your argument by n. We are not going to derive the formula, but we'll be using it to do some examples. So we have the example 1 plus square root 3i, it's taken to the power 4. Again, if you do this manually, it can get a little bit messy. So first things first, convert the complex number to polar form. Again, to do that, you need two things. You need the argument, you need the modulus. The complex number is in the first quadrant, so our argument is there, and this is simply calculated by arctan of square root 3 over 1. And our correct argument in this case is pi over 3. And then the modulus is the square root of the real part squared plus the imaginary part squared. And this gives us the solution of 2. That means that when we apply the Moever's theorem, the modulus will be taken to the power 4. And your argument will be multiplied by the value n is equals to 4. Thus, we have z to the power 4 in polar form as 16 cos 4 pi over 3 plus I sin 4 pi over 3. In most cases, they'll ask you to leave your answer in standard form, so the idea is the same. The fact that a is equals to r cos theta and b is equals to r sin theta. R is equals to 16, cos theta is that. So you take the product to get a. B is equals to sine 4 pi over 3, and then you take the product with 16, and then you will get a complex number in standard form. And then next, we will look into the roots. Now, since we are able to define complex powers, we should also be able to define complex roots. So if you have the complex number z is equals to r cos theta plus I sin theta, and there's the complex number w is equals to s cos psi plus I sin psi, and w is taken to the, w to the power n is equals to z. We want to find the complex number z such that wn is equals to z. This is just, if you take the nth root on both sides, you see that w will be the nth root of z. So from here, the derivation is straightforward. To equate the two complex numbers, since they are the same, they should have the same modulus. That means s to the power n must be equals to r, n cos n psi is equals to cos theta, which means that n psi is equals to theta. But since the argument is not unique, you can add 2 king pi, then this is equals to that. That means that from there, we should be able to derive the formula for the complex roots. And this will be given by the nth root of r times cos theta plus 2k pi over n plus I sin theta plus 2k pi over n. And k is any values from 0 up to n minus 1. So if they want the complex square root, or the complex square root, it means that n is equals to 2. So you will use this formula to calculate by letting k equals to 0 and k is equals to 1. If they want the 4 complex root, it means that n is equals to 4. In this case, k runs from 0, 1, 2, 3, and then you have your 4 roots. So we can look at an example here. We were asked to find the cube root of z is equals to I. If you remember, we said that if, or rather for z equals to a plus bi, if a is equals to 0 and b is positive, then our complex number lies on the imaginary axis, or the positive imaginary axis, and this angle is just pi over 2. So we already have our argument, And we need to calculate the modulus R, which is here the real part is 0. So you have 0 squared plus the imaginary part is 1. So 1 to the power 2, and the answer is positive 1. Therefore, you should be able to express this in polar form. The complex number then becomes, once you have the value of R and theta, you should be able to substitute here for all the values k equals to 0, k equals to 1, k equals to 2, and find your cube roots. So if k is equals to 0, we see that the first root is calculated or is given as that. If k is equals to 1, the second root, when you substitute, you get something like that. If k is equals to 2, then for the third root, when you substitute, you get something like that. As I said, in most cases, they'll ask you to leave your answer in rectangular form. So the only thing that you need to do here is to use the fact that a is equals to r cos theta and b is equals to r sin theta and get the values of a and b. So for W0, this simplifies into minus square root 3 over 2, positive square root 3 over 2 plus 1 over 2i. And for W1, we get minus square root 3 over 2 plus 1 over 2i. And for the third root, we get minus I. And I think that brings us to the end. Again, many things are assumed. So if you're not comfortable with things like the radians and converting from polar form into standard form into polar form, then yeah, you can give it a hit. I think the recommended text will be James Stewart, yes. So yeah, we can stop. Sorry, do we have any questions then?
There are no questions on Facebook.
Okay. Right, so I think if there are no questions, then yeah, that brings us to the end of our session, and then we'll meet again tomorrow, same time, for the next topic.